In this video, I'm going to go over the skills with examples that you need to be able to resolve any vector into its x and y components. Wherever there's a force, which is just about everywhere in physics, there's a vector.
A vector is something that has size and direction, which you probably know. So classically, it's just drawn as a kind of a line with an arrow. So obviously it has size. We could write 10 newtons. And the direction there, well, the direction is often given by some kind of angle, perhaps theta there. But breaking it into its components, what is that actually about? The way I always teach this is to consider that you're going for a walk and you start at point A, you're going to end at part B, and obviously there's loads of ways you could go from A to B. I mean, you could do something ridiculously silly like that. I mean, why would you? The quickest way is along our vector, but what you can consider doing is moving along the blue arrow to start with and then going up a green one like this. Now what you've done there is create two other vectors, the green and the blue one, separated by an angle of 90 degrees. And what we're doing there is we've broken our red one down into its two components. Now, one of the things that you may remember from sort of GCSE type work is that you're allowed to move vectors around. And so let's just take this green one and move it across. And what we can see is that effectively we have lined up our green and our blue along the axes of a graph. And this is where this idea that we get, we're talking about the x component, well, that would be the blue one. This is where this idea comes from because it's lined up perfectly along the x-axis or the y-axis, as you can see. Now, what you have to remember, of course, is that in reality, the green and the blue don't exist. There is only the red, but they act as if there's a blue one across and a red one up. And the great thing about doing this components, or doing it into its components at 90 degrees, is that two forces at 90 degrees have no effect on each other. They're completely independent. We have something like a boat. It's always a boat, isn't it? And the boat has got a motor in it, so it's creating a thrust or a forward force. I don't know, let's give it a number, 100 newtons. But at the same time, the water that is going through is creating a force pushing on the boat like this, shall we say 30 newtons. And then the question wants you to say, what's the final force acting on the boat? Because our two vectors are at 90 degrees to each other, we can just move that tip to tail, draw on the resultant. Then you can just use Pythagoras there and do your Pythagoras rule to work out the size of that. You could then do some trig to find this angle. So let's first look at finding the blue one, which we could call the x component. Well, you might have noticed that in our diagrams like this, the red is always the hypotenuse. We can say that this red is the hypotenuse, theta, down here. If this is the case, then you remember from your kind of trigonometry stuff that the blue one is the adjacent because it's next to the angle. And of course we know that the cosine of theta is equal to the adjacent over the hypotenuse. This means that using this little formula we can take this hypotenuse and bring it up there, and a, the length of the adjacent there, which is our x component, is going to be h, the hypotenuse, times cos theta. Often, but not always, that would be written as f subscript x. That means the component of force in the x direction is equal to h cos theta. So by a similar sort of argument, this over here is going to be the opposite. I remember that sine theta is the opposite over the hypotenuse. So we can take the h, just like we did before, pop it up there. So h sine theta equals the opposite. H, of course, being our vector, which might be, in this case, let's say it's a velocity of 5 meters per second. So therefore, that means that the velocity in the y direction, which is our our opposite, is going to be v sine theta. We've effectively written out the two formulas that will give you your x and y components. And we have a car, there it is, that's driving in at 30 meters per second, has a mass here, and it's going to crash into this safety barrier. And it says calculate the component of momentum of the test vehicle along the safety barrier. Now the safety barrier is obviously this line here. Now momentum is given the symbol P. So we could say we're after P in the X direction. That's what we're trying to find. So let's bring out the vector. And of course it's 30 meters per second. And we know that we have this angle here of 20. So let's just think about how we would break this vector down into its two components. Well, start here, because that's where the vector starts and the vector ends there. Go across and go down. So if the blue one is V, then this will be V in the X direction and this will be V in the Y with our right angle. Now we're interested to find the momentum along the safety barrier, which is in the X direction. So we need this vector here. By similar triangles, if this angle here is 20, then that means that that one there is also 20. So what we're looking for is, remember the V, the actual vector is the hypotenuse, so we're after the adjacent. And we know that cos theta equals adjacent over hypotenuse. So in our formula, we're going to be using cos. So that means that the component of the velocity along the X direction is V multiplied by cos 20. Okay, so if you wanted to put the numbers in, is that the component in the X direction is 30 cosine 20. Now, for those of you that are keen, which of course is all of you if you're watching this, then we need to find the momentum. But we're only interested in the momentum in the X direction, so we need the velocity in the X direction. So that means if we substitute those in, momentum in the X direction is the mass, which is 1.5 times 10 to the 3 times 30 cosine 20. And you shovel that jolly lot into your calculator, and quite frankly, I don't know what you get, but you'll get the right answer if you type it in right.
The next video in this series, coming in a couple of days, goes over a much harder question that you should be able to do now that you've covered this video, unless you don't see the trick.